Hi guys, I was hoping to be back with you today, but my quarantine actually ends at the end of the day today, so I will be back with you tomorrow I'll be back on Thursday in school and Friday, so if you need anything or you want to turn something in or whatever, you should be able to contact me then. Otherwise, you guys will be hanging out with Miss Wood today, hopefully. She has a take-home quiz to give to you, so make sure you catch that before the end of the day, and that will be due on Friday. Normal take-home rules, so I'll just remind you of that at the end. You guys are going to watch a video on 14.3 here. I'm hoping it's short enough, we'll see when we're done, that you can also catch a little bit of 14.4. So that's the plan for today. So today we're going to learn something about how to calculate work through a vector field that has a special property, so specifically a conservative vector field. It allows us to take a few shortcuts, which are convenient because sometimes the work integrals can get kind of ugly. So just a friendly reminder about a conservative vector field. So a conservative vector field has some potential function that it came from. So it's like the gradient of that, right? It's the partial derivatives here. And so to check if something was a conservative vector field, if these are already first derivatives, we kind of took their second derivatives with respect to the other variable because we knew a theorem from a previous unit that said if we take a partial with respect to x and then y, it should be the same as if we did the other order, the partial with respect to y and x. So since these are kind of first derivatives already with respect to x and y, to test if something is conservative, we just take their derivatives with respect to the other variable. So this m function, if it was already a derivative with respect to x, we're going to take its derivative with respect to y, which gives me 2x. And then I'm going to test my n function here, so this derivative of this guy with respect to x, that gives me 2x plus 0 there. So these are the same. So yes, this field is conservative. Okay, so we are going to take this conservative vector field and we are going to try to find the work done to move an object from 0, 0 to 1, 1. And we're going to move it first along this line y equals x, and then we're going to try a few different paths and kind of see what happens. So if we start with the path y equals x, I'm going to use just a nice simple parameterization here with x equals t and y equals t. And if I'm going from 0, 0 to 1, 1, then obviously t will be over the interval from 0 to 1 as well. Okay, so I'm going to use the r and the r prime notation here. So my r function is just my x and my y functions in ij notation. And if I take the derivative of that, that's just going to give me I plus j. And then the next thing I'm going to do is I'm going to find my force function as a function of t. So right now it's a function of x and y, but I'm going to use x equals t and y equals t and substitute those in. So this will look like 2t squared I plus t squared plus 2t j. Right, so I'm just plugging in these into this. Okay, so work is the integral of the force dot r prime. So I'm going to find that dot product next, and then I'll go find the integral of that. So if I dot product those, I multiply their I components together, so that'll give me 2t squared, plus I multiply their j components together, so that'll give me t squared plus 2t. And that simplifies just a bit to 3t squared plus 2t. So then work is the integral of this. I already figured out my t-bounds were 0 to 1. And I integrate that, I get t cubed plus t squared from 0 to 1. And I plug in 1, I get 2. Minus if I plug in 0, I get 0. So the work done to move an object through this field from 0, 0 to 1, 1 is 2. Okay, so we are going to try the same problem again. We're just going to travel along a different path this time. So instead of going straight along the line y equals x, we're going along this curve, x equals y squared. And to do that, we can use a couple different parameterizations. I mean, I suppose there's infinitely many. But the two I think that usually occur to me is, since this is x as a function of y, I might prefer to write y as t, and therefore x is t squared. So that's certainly a parameterization that would work. Or if you just really like x being t, because that's one we use a lot, if x is t, then y squared is t, so y is the square root of t. That also works. And if I'm considering this red parameterization here, if I'm going 0, 0 to 1, 1, that is still going to take me from t being 0 to t being 1. And if I use my green parameterization, it just so happens we are still going from 0 to 1. That is not always true. So you should kind of verify, do your t coordinates work with the x and y parameterization that you picked? Okay, so either of these work. We should get the same answer at the end. So I want you to turn to your neighbor. I want one of you to pick the green one and one of you to pick the red one. And I want you to go through and do the process we just did. So find r prime, find f. Do all of those off of your parameterization, dot product them, find the work by integrating. And we should get the same thing. So go ahead and pause the video. Each of you find your own. I'll put the work down at the bottom here and you can check when you're done. Okay, hopefully you've done all the work now. So just to shortcut the process a little, if you picked this parameterization here, your integral should have ended up being the integral from 0 to 1. I think we get 5t to the 4th plus 2t, which integrates to t to the 5th plus t squared from 0 to 1, which still gives us 2. And if you pick my red parameterization over here, let's see, I ended up with the integral from 0 to 1 of 5/2 t to the 3/2 plus 1, which integrated to t to the 5/2 plus t. And this still gave us 2. Okay, those definitely should always be the same, right? So that was along the same path, just two different parameterizations, and those should always give you the same answers. It is interesting that we happen to get the same answer as if we took a different path back here when we did y equals x. So that's not always true, but it did happen to be true in this case. Okay, and here's a third path just for fun. So we'll try this guy. We're going to do y equals x cubed. So this time if we let x be t again, maybe it's probably the most obvious, then y can be t cubed. And we'll just do that one together. If you already know what you're doing, just go ahead and crank it out. Maybe I won't talk for a minute as I set all this up, and you can just check how you're doing. Okay, so when I set up that one, I did get a whole different integral, but I keep producing this 2 as my final answer. So by now you should be kind of suspecting that something is going on. There's a theorem that says the work done by an by a conservative field is independent of the path taken. So we could have taken any of those paths. As long as you are in a conservative field, you will get the same result. We're going to learn something next called the fundamental theorem of line integrals. That sounds really important. Maybe you vaguely remember last year learning something called the fundamental theorem of calculus. And it says something amazing, which just says if you take a derivative and an integral of a function, you get back to the function. Which is maybe not that amazing because you just know the mechanics of how it works, but that's what the fundamental theorem of calculus says. So the fundamental theorem of line integrals actually is a similar thing. It only applies to conservative fields. And it says if you're going to do this integral, which is f dot r prime or dr, if f happened to be a conservative field and therefore f is like the gradient here of some potential function f, when you integrate the derivative of that, you should just get back to f. So this fundamental theorem of line integrals says that if you knew what f was, the potential function of f, then you don't have to take a derivative and an integral. You can just figure out the potential function, and you can just plug your final point minus your initial point, and that'll give you the work done in moving an object through the field. Okay, so the little note down here just says this should remind you of the fundamental theorem of calculus, right? Because we're doing an integral of a derivative and we're getting just back to the function. So that potential function f here. Okay, so obviously that's only going to work for conservative vector fields because they're the only ones that have a potential function. So hopefully that is not a restriction that you'll forget about because it won't work if you can't find a potential function. Okay, because you're not tired of this same exact example again, we're going to just do this one more time using the fundamental theorem of line integrals instead of going through a particular path. We're just going to find the potential function and then evaluate it at our points and subtract them and hopefully get the right answer. This is the same problem I made you at the very beginning check to see if it was conservative, and we took the partial derivatives and it was, so we should be able to find a potential function. So to find the potential function, I need to integrate kind of the pieces back. I'm going to use a notation. This is just Miss Robbins' notation. This isn't like a real life notation. Where I'm just kind of finding the pieces of the potential function. So I'm just going to label them with parts for now, like a P1 and a P2, and then I'll just throw those all back together when I get my final potential function. So if this was the gradient of some function, this 2xy was the derivative with respect to x. So I want to integrate that with respect to x to go back and figure out what was my original function. So if I integrate that, hopefully it makes sense here, we're getting x squared y plus c. And we've talked about this before, but just friendly reminder that the c function there, that could be a function of my other variables or a constant or some combination. Okay, and then I'm going to take my j component over here, and I'm going to integrate that with respect to y. And that should give me more pieces of my potential function. So I integrate x squared with respect to y, that gives me x squared y. And I integrate 2y with respect to y, that gives me y squared plus c. And once I have all my pieces, when I combine those, any term that had x's and y's in it should be showing up in both of them. Again, that doesn't mean there's two. It just means when we took their partial derivatives, right, the partial derivatives, it kind of showed up in both pieces as it should have. So my whole potential function is x squared y plus y squared, and then still possibly plus some constant. So the fundamental theorem of line integrals says if I take this potential function and I just plug in my final point minus plugging in my initial point, that should give me the work done through this field. So if I plug 1, 1 into this, to my p function up here, I get 1 plus 1 plus c. And if I plug in 0, 0, I get 0 plus 0 plus c. And my c's will cancel out and I'll just get the 2. So random thought real quick about c. So if you're writing a potential function, you should put the plus c in there. When you're doing this part, This is like a top bound minus bottom bound kind of idea when we evaluate integrals. And these c's will always end up canceling each other out, right? So usually when we do like a definite integral, we don't ever put the plus c in there. So you don't necessarily need to put the plus c in here as well. If it says what's the potential function, we should include it. But if we're finding the work done and you skip the plus c, that's fine. Okay, hooray, we got 2 again. So we keep getting the same answer of 2. We went all kinds of different ways. We used different functions and we keep getting 2. This next slide just says that we could do this in 3 dimensions as well. So if you have a vector field in 3D space, you can still find a potential function in 3D space, right? You're just evaluating the functions with 3 variables instead of 2. So nothing really exciting to be seen here. Okay, we're going to try another problem in case you're tired of the first problem. This guy does have an ijk component, so we're in 3D space. And if I want to use the fundamental theorem of line integrals, I technically should check to make sure the field is conservative before I do so. And like I said, if you don't do this, really you won't be able to find a potential function, so it'll probably work itself out anyway. But just for good math, I'm going to call these M and P and find their partials. And maybe I'll find a couple of them and make sure they're the same, but there's lots to do with something of 3 variables. So if I want to take the derivative of m, say with respect to y, it should match the derivative of n with respect to x. So that happens to be 0, that happens to be 0, those do match. You could test m with z and p with x, right? So we're kind of crossing these two together. So m with respect to z is 0, p with respect to x is 0. And we could try n with respect to z and p with respect to y. And n with respect to z happens to be 1, and p with respect to y happens to be 1. So everybody matches, it is conservative. Okay, so if I want to use the fundamental theorem of line integrals, then I want to find the potential function. So I'm going to integrate these pieces one at a time. So I'm going to start with my I component there. So the integral of negative sine of x with respect to x is cosine of x plus c. And then I'm going to do my j component, which was just z. So I'm going to integrate z with respect to y. I get yz plus c. And then I'm going to check my z component, or my k component, excuse me, which was y. So I'm going to integrate y with respect to z, and I get that yz term again. I should get that twice because it had 2 variables in it, right? So it should show up in both of those. And knowing all those pieces, then my final potential function is cosine of x plus yz plus c. So if I want to find the work done from 0, 0, 0 to pi halves 3, 4, I'm going to plug in my final point minus plugging in my initial point. And I'm going to skip writing the c because those should all cancel out. So if I plug in pi halves, I get cosine of pi halves, which is 0. And then plus y times z, so 3 times 4 is 12. And if I plug in 0, 0, 0, I do get something here, so don't skip this. So the cosine of 0 happens to be 1, plus yz is 0. So I get 12 minus 1, which is 11. Okay. So there is a theorem too that says maybe what we kind of discovered earlier, that if you want to find the work done through a field, it happens to be independent of path if and only if the field is conservative. So that if and only if means it's in both directions. So we kind of, because of the fundamental theorem of line integrals, if you evaluate just a final point minus an initial point, it didn't matter which way the path went, right? So that should be kind of obvious. And then the proof in the other direction says if the field is conservative, then therefore it must be independent of path. That's shown in your book if you're curious about it. But those are both kind of binding. So if you know one thing, then you know the other thing. It also gives us kind of a convenient thing that says if you want to find the work done in moving an object through a closed curve, so in other words, you start somewhere and you move and you travel back and you end in the same spot. If you went through a conservative vector field, then the work done for that must be 0. And hopefully this makes sense to you. If we evaluate our potential function at our final point minus our potential function at our initial point, right, those should be the same exact thing, right? Because you're plugging in the same point, so we should get 0. Okay, so therefore we get that all three of these things are really equivalent conditions. So the field is conservative, the work done through it is independent of the path, and the work done through a closed loop or closed curve is 0 for every single closed curve in the plane. Okay, if you want to write that down, you can pause it for a minute. Okay, so I'm going to walk through another problem that is kind of similar to what we started with, just talking about some different ways, because sometimes one way or the other way might be easier or harder. So we're going to start with a function here, and we are going to use this parameterization they gave us, and we're just going to set up our normal integral for work done where we take f dot r prime and we set up that integral and see if we can evaluate it. So we're going from 0, 0 to 2, 0. We are taking this path here along the curve, and we're using this parameterization that they gave us. Okay, so if I set this up, if that's r, then r prime is sine of t I plus cosine of tj. And then I need to write my force, which was this thing, and I need to write that as a function of t. And so I'm plugging in for x, this 1 minus cosine t, and for y, this sine of t. So it's going to look a bit messy, but let me try to write all that out. So y is sine of t, so this will look like sine cubed of t. And the next component was, let me jot this down so I have room to work, 3xy squared plus 1. So I'm going to plug in all my components here. Is it 3xy squared? Yeah. So I'm going to have 3x is 1 minus cosine of t. Y is sine of t, so I'm squaring that. Plus 1. Okay, so my work done. And if I'm going to go from 0, 0 to 2, 0, then if I'm going to go over here to 2, if I set this 1 minus cosine equal to 2, right, because x is ending at 2, I get cosine of t equals -1. And so then I've got to end with t being pi. So I would integrate from 0 to pi of f dot r prime. I wrote all those in t so I could find a dot product. And I'm already thinking to myself, well, that looks terrible. I don't really want to do that. This does not seem like a good parameterization. If this field is conservative, this seems like a bad way to go. So I could do it, but I'm going to stop there and decide not to. Okay, so if it is conservative, we could instead go at a path that goes straight from 0, 0 to 2, 0, and that might be a much easier parameterization, so I'm going to try that and see if I like that better. So if I'm going to go straight along this line here, right, then I'm going to use the parameterization that x equals t, so that'll send me straight across, and the y-coordinate the whole time is staying 0, so I'm going to let y be 0. And if I travel from 0, 0 to 2, 0, then my t interval will be 0 to 2. And I'm just thinking that's going to produce a way nicer set of functions here. Okay, so then my r function, is ti plus 0j, which means my r prime is just I. So that seems friendly. And then my force, if I scroll up here, was y cubed plus 1. So remember y is 0. So this is just going to be 1i. And plus 3xy squared. Again, since y is 0, that's going to zero out that whole thing, and I'll just get 1j. And I'm feeling much happier about this, right? So I think this is going to produce a nice integral for me. So if I do f dot r prime, I multiply my I components here and I get 1, and my j components I get 0. So this is just 1. So I can integrate. I figured out my bounds were 0 to 2 in t's. This whole integral just becomes 1. So I get t from 0 to 2, which is 2. This is different than the other problem, by the way. Just happened to come out as an answer as 2 again. Okay, so I really kind of liked that problem using that path. So if you can think of a smart path that's going to save you lots of work, go for it. We're going to try the same problem again using the fundamental theorem of line integrals. And so that is finding the potential function and doing final point minus initial point. That's usually pretty friendly to do too, but sometimes if you find a smart path, that might actually be your better option. So it's just up to you what you like to do. So I'm going to find my pieces of my potential function like normal. So from my I component, if I integrate y cubed plus, that's a cubed, plus 1 with respect to x, I get x y cubed plus x plus c. And if I integrate this j component with respect to y, let's see, I'm going to get that xy cubed piece again, and then plus y plus c, which means my whole potential function has that overlap term, and then it has these separate x and y terms, and then maybe some constant. Okay, so if I want to find the work done, I can do this potential function. I was traveling from 0, 0 to 2, 0. So take my final point minus my initial point. And if I plug 2 into this, I'm going to get, let's see, my first term here, I'm going to get 0, because y is 0. And then I get the 2 for the x and a 0 for the y. And if I plug in 0, 0, I get a whole bunch of zeros. And so I just get 2, which I was expecting because I did that a different way in the last problem, or in the last path, and I got 2. Okay, so last time we did this workbook, I want to say it was page 90, I don't remember, maybe 4 or something. You guys worked on this hopefully last class. And I told you to skip kind of the very last function down here. So there was this function, maybe you did part A. So it said find the potential. So if you integrate each of these pieces, if you integrate that one with x, you get an xy. If you integrate this one with respect to y, you get a sine of yz plus z. And you integrate, whoops. I kind of drew this in a weird spot, sorry. That was still part of the j term. Okay, and then we're integrating x with respect to y as well, so we get that xy term again. And then if we integrate this guy with respect to z, we get sine of yz. So we can see our overlap pieces. So our potential function is xy plus sine of yz. Okay, so you might or might not have done that last class, but that's our potential function. And so I wanted you to not do the rest of this problem yet because we want to be able to use this. If it had a potential function, it's conservative. And so to find the work done, then we'll be way faster using our fundamental theorem. So our work done should be our potential function at our final point. So we're moving from this point to this point. So this is our final point minus potential at the initial point. Okay, so let's plug in all our numbers. So if I plug in x and y are 1 here, this gives me 1 plus sine, this will be sine of pi over 2, which is 1. So that's plugging in this point here. And then I want to do minus plugging in this point. So if x is 0, that first term will be 0. If y is 1 and z is 3 pi over 2, then that'll be sine of 3 pi over 2, which is negative 1. So this will give me 2 plus 1, which gives me 3. And the last function says find the work done by F in moving a particle around the unit circle once counterclockwise. So if you think about this, if we move around the unit circle once, we're going to end up back where we started. So what does that mean the work done is? So the answer to that should be 0 because it's a conservative field and we're doing final minus initial, so we should end up with 0. Okay, the video is gonna stop here. I'm gonna go ahead and do a little video on the next section too, which is 14.4. So I want you guys to watch that. If you don't get through the whole thing, that's fine. You guys can let me know on Friday. You can pause it wherever you are. But at some point today, make sure you pick up the Unit 5 quiz. So take that home with you. Normal rules about quizzes. So you can use notes, textbooks, any resources that I provide you. And you can use your peers on this quiz. It is due Friday of this week, so make sure you bring that with you. Okay, thanks. Have a great day.